Hi everyone. Now that we've reviewed linear functions, I'd like to get into what is probably a more realistic situation where instead of being given 2 points that are perfect for your line or a point and a slope, what you actually get is a data set, and it will be imperfect, and we'll be looking to see if we think there's a linear trend and then doing our best to find a linear equation that represents that trend that we think we're seeing. So our data set gives the reaction time of an astronaut that has spent however many hours weightless. So the first thing I want to jump into is this part A. We're going to head to Desmos and create a scatter plot there, and then we'll talk about trying to fit a model to that in a couple of different ways. I would like to point out you can absolutely also do this pencil and paper, and for a test, if you're asked to do that, you'd then just scan and upload that picture. Otherwise, from Desmos, you would take a screenshot and upload that. Okay, so let's go over to Desmos. I'm going to try and keep this up as well. So here's my desmos.com. I'm going to go to the graphing calculator, and sometimes you can actually just cut and paste a table over, but I'm just going to assume that we can't. So you can always try that, select your table and try just Control V to paste it over here. Otherwise, you're going to hit that little plus button and you're going to add a table, and we're going to add our hours weightless. And just type all of those in very carefully. If you type data in incorrectly, your results will not work out quite as you expect. Okay, so reaction times 0.7. All right, so there it is, and let me just do a quick double check. 1.26, 62, 42, 47, 8502, and 93. All right, so there it is, and I'm going to hide this since my window is a little bit small so you can see better. So Desmos is fairly intuitive. You can drag your graph around to try and get that data to fit within your window. That's a little small, so you can pinch to zoom if you're on a device that allows you to do that. And we're basically just trying to get a nice window to see the trend in the data. So there's my data, and I tried just zooming in and out a little bit and messing with it, but I still don't love the window. So I'm actually going to play with that. I think the X values aren't bad. I'm seeing 0 to 15. I maybe don't need to see 0 to 5, but it's fine. But let's play with Y values. So if you hit that little graph settings button, let's see, you can play with a lot of this stuff. You can add labels. So our x-axis actually represents hours weightless, and our y-axis represents reaction time. And then I don't need to see anywhere close to this much stuff on the x-axis. I'm going to go negative 0.5. You could go 0. It just kind of makes the graph look nice when you can see the numbers below the axis. And then it looks like around 2 is my biggest, so I'm going to say 2.5. And you can even set your step. So it looks like it set it to be 0.5, 0.51, 1.52, 2.5, but you can set that manually. Sometimes it won't listen to you if you try and make your tick marks too close together, but you can absolutely play with it. Okay, just checking out more options to see if they added anything. So here's my data set. I'm liking it. Now I want to think about trying to fit a model to this. So I'm looking at it and I can kind of imagine that a straight line would fit through and be fairly close to those points. And one of the ways we can do this is just by eyeballing it, which means on a pencil and paper, you would draw this and then set down a ruler or something and kind of tip it until you think you've got a line that goes through the data, and then draw that line in. If you're going to do this in technology, we're going to go ahead in here and we're going to say, all right, let's make an equation, y equals. I'm just going to start, let's say the equation goes through the origin, and then we want it to go over 15 up about 2. That's really rough, but we can play with it. So rise to run 15 x. And that's actually not too bad, but we'd like to mess with it. And I don't know, 2/15 doesn't seem that easy to mess with. So you could go ahead and plug that in your calculator, or just sort of estimate. What I'm thinking here is if it was 3/15, that would reduce down to 1/5, which is 0.2. So I'm actually going to start with a decimal here. Okay, so that looks a little too steep. So maybe I'll go 0.18 or 0.16 or 0.15. I'm kind of liking that. The other thing we could play around with is it doesn't have to go through the origin. We could shift that y-intercept up a little bit, maybe 0.1, and then lower the slope. And again, this is an eyeball best fit. So you're not going to get necessarily a perfect fit, but you just want to get something that captures the pattern that you think you're seeing. If you've drawn this in on paper, you will have to then find the equation. So what you'd want to do is look at your line and try and find a couple of points. So for example, this goes through 0.1. Say we didn't know the equation, we could take that, and then we could estimate it looks like it goes through 5.8. And given 2 points, you can find the equation for the line. So it's entirely up to you if you want to pencil and paper draw this or use technology for the eyeball best fit. But that's how I would do it with technology. Okay, so back over to our directions over here. When we do the eyeball best fit, we get y equals 0.14x plus 0.1. So again, everybody's answer could be a little bit different here, and I will give you some wiggle room for that when I'm grading things, but we should all be sort of in the same ballpark. Next, I want to show you how to actually get Desmos to tell you what it thinks the best fit is. And again, this would depend on how you define best fit, but the way Desmos defines it is the least squares. So it takes the error associated with each point and it squares it and it does some things, but it tries to minimize the sum of the squares of those errors. So it's going to be a little bit prone to outliers. It's not the only way to do it, but it is by far the most common. And Desmos is fantastic. It does this in such a nice way. So you just have to remember how to ask for it. So you want to look back up at your table and say, okay, my y values in my table are y1s and my x values are x1s. So instead of typing just y, we're going to type y1. And I literally just typed a y and a 1 to get that. And it knew to make that a subscript, which is really nice. And then we're going to leave this a variable. We're going to say, oh, hold on, I did one thing wrong already. You don't get to put an equals in, you have to put a tilde in. So you do that. That's what tells it, Desmos, it's your job to fit a line to this, or whatever sort of function we ask for. All right, so instead of us guessing what the slope should be, we're just going to leave the variable in there. So I'm going to use m, but you could use something else. Don't use x or y. You pick what you want, but m seems pretty easy. And then we want this to use the x1s, so we'll type in x1. And then we also want it to see if we should have a y-intercept, so we'll put a b in there. And you can see it drew it in purple. It just automatically went in and did its sums of squares of errors, and it minimized that. And it doesn't look too far off from what we got. So we thought our slope should be 0.14. Desmos thinks it should be, I know that little keyboard is right in your way here. We'll make this big for a minute, see if it's better. There we go. Desmos thinks the slope should be 0.135-ish. We thought our y-intercept should be about 0.1. Desmos thinks it should be about 0.157. So I think we did a pretty good job. We being me, good job myself. But this is going to be something you're going to try as well. You're going to try and estimate what the line should look like and then check yourself to make sure you kind of got the feel for how this should work. Okay, so back over here, I'm going to say that the least squares is what it's called. I'm actually not too worried if you don't remember that, but when we do linear regression, it's called the least squares line, is y equals 0.135x plus 0.157. Okay, so this is our equation according to technology. All right, one other thing I want to point out while we are in Desmos still is the R and R squared values. I don't need you to memorize this bit, but I do want you to have the general idea that these tell you how well your model fits the data set. So really specifically, the R squared value tells you what percentage of the variation in reaction time is caused by variation in hours spent weightless. So we're looking for numbers really close to 1. If we've got an R value equal to 1, that means 100% of the variation in reaction time can be attributed to variation in hours spent weightless. That's a perfect fit. So it's probably not going to be 1, but we'd like it to be close to 1. The R value, something that's nice about that, you might get asked for either of these as you work through homework, is it can be positive or negative since it hasn't been squared. So you will also see that the sign of R changes. If R is positive, then you've got an increasing trend, a positive slope. And if R is negative, you've got a decreasing trend. You've got a negative slope. So do pay attention to those. We like to see values around 0.9 or higher. And what that tells me, this is just a little bit of vocab in here, is how confident I should feel about extrapolating. So we can do interpolating, which is making predictions within the data set. So here we have data about reaction time between 5 and 14. We would be interpolating if we plugged in any number between 5 and 14 and used the model to make a prediction. Extrapolating is plugging in numbers that are outside of that data set. So if we wanted to plug in 16 or 17 or 18, that would be extrapolating. And the higher your R and R squared are, the more confident we can feel about doing some extrapolating. Always, as we start to get really far from our data set, we should feel really nervous about making predictions. But with strong R and R squared values, we can feel a little better. Last thing I'm going to show you, we're not going to mess with this a lot this quarter, but I do want you to see it, is you can plot residuals, which are the errors. So what you're seeing here is how far our points are from the line. And the reason that this can be interesting is if you see a pattern here, if this looks curved up or curved down, that means that your straight line is not a great fit. It would be better to use something curved. So that is something that we can play with a little bit. We won't do a lot, but we can mess with it a little.